Welcome to APEC. It's October 9th, and I'm your moderator, Tim Ventura. First, I'd like to thank everyone for joining us on this call, along with everyone watching us on YouTube. In today's session, Steve Burns will be discussing UAP Spectral Shifting and ELF gravity control. Peter Reali and Rich Hoffman will be discussing the Scientific Coalition for UAP Studies, and Charles Crawford III will be discussing the Graviflyer he purchased from Alexey Chekurkov. We'll also hear updates from Falcon Space and Associates, and we will be finishing off the event with an open discussion and ad hoc presentations by conference attendees. Okay, so let me give you a couple of quick reminders. You can view conference replays, details, and speaker info on our website at www.altpropulsion.com. Now, Jeremy Reese will be streaming today's conference live on YouTube. Mark Sokol will be streaming live audio only on Clubhouse. And I'd like to invite everybody to join our APEC 24/7 channel on WhatsApp. I pasted the links into the Zoom chat already, and you can find more info on the contact page of our website as well. So please save your questions for the Q&A session after each presentation. Please raise your hand in Zoom using the option Y on Mac or Alt Y on Windows. You can also type those questions into chat, and we'll go through them after each presenter finishes. Okay, now let me introduce you to our first guest. Steve Burns is a retired nuclear engineer working on Professor Fran De Aquino's System H ELF gravity control model. Steve is one of 3 engineers that developed the first ATL medical color flow Doppler ultrasound and has an extensive career in software and network design and engineering, which includes mobile interface for the energy smart grid, software for thermal neutron density logging, and fission counter monitors for nuclear reaction status during reactor core restarts. He is joining us to discuss spectral shifting in UAPs and describing his gravity modification experiments. So without any further ado, let's welcome Steve to today's event, and I will hand it over to him to get started.
All right, I'm calling it electromagnetic radiation mass shift and space refraction theory. And it's part 2. I had a presentation about a month or a half ago where we talked about the experiment that I'm working on. So if you want information on that, just look at the first presentation. I also went through a history of this theory and also went through some of the antenna theory on it. This presentation is moving on. We're going to start where that one left off. It's all new material. And hopefully by the time this presentation's over, you're going to understand exactly what this theory is from an atomic level all the way to how a gimbal works. We're going to split hairs with gimbal. All right, let's go here. So what we're going to discuss is, I'm going to go through a quick theory summary. It's not going to be as extensive as the first lecture. If you want a more detailed, just watch that one. This one's going to be just touching on some of the points, and I've got to get through some of the equations because that's what this presentation is based on. Everything in this presentation is about this theory. I'm looking at the equations of this theory and I'm seeing what they say, and that's all I'm doing. And really, that's all you need to do because this theory just keeps on giving. I've been involved with it for 20 years now, and I'm still discovering new things. I discovered something a few days ago about inertial mass, which I'll present to you. And I don't think it's ever been published before. So what we're going to do is we're going to look at the negative mass curve, and we're going to contemplate control theory on that. We're going to look at diametric tilt flip vector analysis to try to understand why somebody would want to tilt and flip. We're going to touch on superconducting antennas. Over the years, I've learned not to use the word antenna, because if you say antenna, people think about their television and they just don't think it's credible. But if you say radiator, it's a mysterious physics thing. And that seems to be okay. So I try to use radiator when I can, but it's really an antenna. They're interchangeable. Then we're going to look at a calibrated space refraction instrument. This theory actually gives you a way to calibrate this instrument, which would be pretty amazing because you could do a lot of research with that. And then last but not least, we're going to look at a electromagnetic radiation detector for the frequencies that I'm working with. And this is based on what Ron mentioned last time in the QA section about Schumann resonance. I realized I can't transmit with that, but I can certainly receive with that. And so what I try to do is come up with my own personal spin on how I would do it. So this is kind of an overview of where we're going here, and we can talk about spectral shift at the end if you want. Okay, why I like this model. The equations reduce properly, all of them. Originators proved it two different ways that agree. DHR used quantum field theory to create the foundation of this theory, and then they backed it up with Feynman diagrams. So they have a two-tier approach that gave the same answer, and there's three of them in consensus. So that is somewhat credible to me. No way discovered inadvertently. Even when you know what you have to do, you can't really get there. It gives good answers describing aerial phenomenon, which we'll discover, and it connects Maxwell to quantum theory. This theory is mostly Maxwellian, but at the same time, it's based on quantum field theory, so you can actually see which part of the theory is which, and I'll show you that. But you have to understand that being Maxwellian, it tells you a lot about how to do it, but it tells you nothing about what happens once you do it. Relativity tells you what happens, but it doesn't give you a whole lot about how to make it happen. So I see those two theories working together, where relativity basically takes over where this takes off. So we're not going to discuss relativity, we're going to discuss Maxwell. So this theory can either be interpreted as a mass reduction theory with space refraction as a side effect. That's what I talked about on the first presentation, and I really tried to avoid space refraction because for several reasons. Number one, it's worthy of a whole presentation. Secondly, I really wasn't prepared for it. I was thinking it was about the experiment I was working on. Or you can see it as space refraction with mass reduction as a side effect. That's what we're going to focus on this time. All right, so we're going to see how space refraction works with this model. So let's go back through a brief summary here, just so we're all on the same page. Last time I showed you the two papers that spawned this effort. Now, for those of you who think that 1986 is dated, let me remind you that Boltzmann's idea sat dormant for 75 years because nobody liked the idea that a probability distribution can provide fluctuations that violate the second law. It wasn't until Planck ran out of ideas that he tried entropy, and of course, quantum mechanics is the result. So yeah, it's been around for a while, but it's theoretical, and nobody really has spent time with this except a handful of us. So the second part here is what De Aquino added to it in 1999. And he basically looked at it and said, well, Lee, let's not constrict it to just thermal radiation. Let's look at it for all radiation. So he derived the general case, and we're going to go through that in detail, so you're going to know exactly what it is. So the important thing about the general case, if you look at the very last lines on here, it talks about the two equations. You have MI and you have MG. Well, it turns out that the MG equation, according to this model, has a subtractive term, the minus sign. And that gives us a way to do what we're doing, because if you can figure out how to make delta M beta change size, you can make MG either go negative or zero. there's nothing special about going negative. You just increase the power so that you go through zero. And as a matter of fact, if you try to control for zero, you'd probably, control theory says you have to have an error to control, so you vacillate between plus and minus mass, and I'm not even sure what that means. So at any rate, there's nothing special about zero gravitational mass, and there's nothing special about negative mass. It's all dependent on how much power you deliver to the radiator. So what we're going to do is we're going to take these two equations down here, and we're going to derive the mg equation from them. So let's do that. So I'm going to leave the equations up at the top so you can see it. So these are the first two equations at the bottom of that last slide. And here's our minus term over here. So what we're going to do, and please bear with me with the math. I've got several slides on this, and we'll get through it, and then we'll talk about the fun stuff. Okay, so we got this subtracted term, and we want to know, and it turns out that this, the delta MB is the mass shift term, which is fortunate because that's what we're trying to do. So what can we do with this mathematically? Well, the first equation, MI, we can solve it for M. And then we can substitute M into the second MG equation, and we get the third equation here. Mg equals Mi minus 2 delta M beta. The delta M zeros drop out. So let's think about delta M beta. Delta M beta is basically the mass shift we're looking at. So it's the delta energy that happens in the system of the atom and the space that the atom resides. I think you have to consider both of them together. And so what this is saying is that you've got some change in energy. Whenever I see an equation like this, and being an engineer, I always like to check units. So if you multiply both sides by c squared, you have mc squared, which is energy, equals energy. So the equation seems right. And so what the theory does is it looks for that delta H that we're trying to discover. So it takes the resultant of the forces and subtracts the original energy from it to get the delta energy. And we end up with this equation. This equation right here on the right is simply the Hamiltonian equation just algebraically manipulated. So it's in a friendlier form algebraically. So you can derive this if you want, but this is what you get. So the important thing right here is the delta P. It's not the energy of the incident radiation or the radiation being emitted. This model either works for an atom emitting radiation or being illuminated by radiation. It's the change in momentum of the atom during that process. So if you substitute delta MB back up into the MG equation, you get an MG equation that contains the delta P. And then delta P, according to the model, equals the energy of the incident radiation or the emitted radiation divided by the phase velocity of the medium that radiation and the atom reside in, which is space. And again, I like to check units. So I have momentum here, which is mass times velocity. And then I have a velocity down here, which gives me mass velocity squared, which is again energy equals energy. So the units work out on this. So if we substitute delta P into the above equation, and we also, I have to tell you that one more equation here, the phase velocity equation that I'm looking at here, this is a Maxwell equation. It's got nothing to do with this model. You can look at EM textbooks and they'll have this. And if you put 0 in for sigma, which is free space, it reduces to 1 over the square root of mu epsilon, which is what people usually think of as phase velocity in space. So if we substitute Vp in for delta P, and we substitute delta P in for the equation above, we get the Mg equation. where U is equal to the incident radiation or the radiation being emitted. And in this case, it's some attenuation factor that has no dimensions, eta, because if you're propagating through a medium that's not space, it's going to have attenuation, so you have to account for that. The power density, which is watts, or excuse me, just the power is, it's watts per meter squared is the power density. So it's how much power you're putting out per meter squared. In an isotropic antenna, it would just be the surface area of the antenna divided into the power that the antenna is radiating. And then we have the cross-sectional area of our target, which in this case is the atom if we're illuminating it, which is meters squared. It's divided by frequency, which is cycles per second. So power density, watts per meter squared, cancels with the target, meters squared. So you just get watts divided by cycles per second. So you end up with watt seconds, which is joules, energy, per cycle, not per second. That's very important. It's per cycle. So if you have this effect occurring at, let's say, 1 hertz, and it takes you 1 watt, just for simplicity, to make the effect happen, and then you change the frequency to 100 hertz, well, right away, you'd have 100 times more power that you would require. Plus, you've got this omega term up here in the mg equation, which gives you another square root of f. So you'd have 100 times the square root of 100, which is 10. So you'd have 1,000 watts you would need at 100 hertz compared to 1 watt you would need at 1 hertz. That's why we're using ELF, because you get more energy per cycle. So it takes less energy. You don't have to have thousands of watts of radiation to see this. You can do it with 10 watts. So that's where the low frequency comes in on this model. It's not that we want to do it, it's because it's the only way we can keep the power required to a practical level. So the mg equation, you can see the -2 mi term here, which is the delta m beta term up in the above equations. So we're basically using Maxwell's phase velocity that we're substituting in for the phase velocity of the energy that's transmitting in the medium around the atom, which is, you know, what it is. So it's sensible to me. So now we're basically integrating Maxwell with quantum field theory. So we have this equation that's dependent on mu's and epsilons and sigmas of the medium that we are transmitting in. And that is the crutch of what we're trying to do here. So let me just move on a little bit. So where does refraction come in? Well, if I look at the model from space refraction instead of mass reduction in space, I can do magic, algebraic magic, like multiply both sides by c to the 4th. And you can rearrange the mg equation into this equation, which replaces all the sigmas, mu's, and epsilons with phase velocity. In other words, we just didn't substitute it in like we did before. We just took the substitution of VP out and we left it VP. So if you do the algebraic magic on this, you can get it in the form where you can get C over VP, which is index of refraction, and that is the form of the equation we're seeing right here. You still have the -2 mi component of this, but now instead of doing it in terms of Maxwell's parms, we're doing it in a more condensed index of refraction form. So, and again, looking at this equation, index of refraction has no no units. U is energy, mc squared is energy. So all of this is dimensionless. So you just have mg equals, you have mass equals mass. So the dimensions work out here. So if you solve this equation for MR, you get this guy. And this is one of the most amazing equations that I've ever seen. So let's just stop and contemplate this equation for a minute. First of all, one thing about this equation, the right-hand side, there's no Maxwell. It's all quantum, 100% quantum. The left-hand side's all Maxwell, no quantum. So we've actually separated the two theories and set them equal to each other. So if you look at this equation from the quantum side, it really is an odd equation, and we're going to explore this equation in a lot of detail in just a minute. But one interesting thing about it is if you set mg to 0, in other words, you control the radiation so that gravitational mass is nulled out, this is a number. So I'm calling it refraction index of 0 mass equals a number times the mass of the element that you're working with. So each element would have a different n0 number. C squared's a constant. Mu 0 is the energy you're providing to it to make it 0. You're doing that. So you know what that is. So you can actually calculate this number for, let's say, iron. I use iron as the example in this presentation. So you can actually get a refractive index of iron that makes the atoms of iron 0 if you could get that refractive index, and of course it would be greater than unity. So let's just spend some more time thinking about Maxwell versus quantum here. So the index of refraction, we said before, was equal to what Maxwell says it is, which is this guy. So this is 100% Maxwell up here. So we're going to equate the NR of Maxwell to the NR of quantum. And we're going to get, see if I can get this to highlight. We're going to get this guy down here on the bottom here. So the left-hand side, all Maxwell, right-hand side, all quantum. So what we're going to do is we're going to take this equation. Okay, by the way, if you combine this back over and you solve for mg, you would end up with the mg equation that I showed you earlier. So it's all the same equation. I'm just looking at it in different ways. So we're going to look at this and see what it means. So let's do a thought experiment here for a minute. Let's take an iron atom. Star went supernova, it spewed out iron, inverse square law, got far enough away, we had no close neighbors. So you just have the iron atom and you have empty space. That's all there is. So now let's say you irradiate that atom with the correct energy and it experiences mass reduction. Well, what do you have to work with that says I'm responsible for that reduction? Well, you have the atom and you have space. So if you drill down through all the equation layers, through the antenna layers, through the quantum layers, through the Maxwell layers, and you just keep going down and down, and you hit bedrock, what you end up with, assuming that you're not changing the conductivity of space, the reason I don't like the idea of changing the conductivity of space is that, number one, you're resurrecting it out of 0. Number two is it would attenuate the electromagnetic radiation that you're illuminating with, so the model would oscillate between masses. And so I'm going to go with conductivity of space staying zero. So we're going to X out sigma as a possible reason why this model is happening. And we're going to focus on just 1 over the square root of mu epsilon. Well, VP is getting lower when we do this. One thing you'll find with the models that are discussed on this forum, reducing phase velocity, changing mu and epsilon of space, and for this model, low frequency, they all seem to be a theme. Well, this model says if you want to reduce phase velocity, you've got to increase mu or epsilon. And that's what's happening with the iron atom. Somehow, the process of the illumination or the radiation is changing the space that the atom resides in. And it's changing it by making either mu or epsilon larger. That's permittivity and permeability of space, which already has a number. You're not bringing it out of zero. You're just changing the value. And they both increase. They don't go negative. There's no negative metamaterials here. The model has nothing to do with metamaterials. These guys go bigger, which makes VP smaller. So I'm claiming that during the process of delta M beta changing a mass shift, somehow space changes its permeability or permittivity. I don't know which one. It could be both, it could be one or the other. I don't know how much. All I know is that that's happening. And so by doing that, we're allowing this process to happen. So the iron atom mass reduction results from a change in epsilon and or mu of free space, since nothing else to work with. Refraction of space changes to allow the process. Well, if you change the VP of space, you've changed the refraction index of space. It's the speed of light divided by VP. So refraction of space got larger. All radiation that we're talking about in this presentation is electromagnetic radiation, and preferably below 2 hertz, definitely below 10 hertz. For above electromagnetic radiation process, epsilon and or mu of free space must change. Sigma must remain 0, or model will oscillate between masses. In other words, you have no mass shift, and then you provide the radiation, you shift mass, now space becomes conductive, now you've attenuated that radiation, now you go back to no mass shift again, and you just keep going back and forth, which is senseless. I'm not sure that has any meaning. So we're going to say that's not going to happen. And okay, now this last part, this bullet right here, is probably the most important thing in this whole presentation. A radiator radiating, or a radiator illuminating a surrounding shield of atoms, forces the above space change process to be continuous while the electromagnetic radiation is present. In other words, we're taking this odd change of space that's happening during this process of the atom, and we're just keeping delivering the radiation so that that change of space continues as long as we are providing the radiation. Energy U is per cycle, not per second. We talked about that already. That's why we're using ELF to get reasonable power densities that we can work with. Okay, this is important too. The last presentation, people were asking me, how long does this effect take to take effect? Well, we talked about, the resonance of the antenna having to charge up to a voltage that allows it to radiate efficiently at the powers you want. So you've got some latency time there where the antenna is building resonant voltage up to a value where it can radiate to the amount of wattage that we need. That's a delay. But once you're there and you sustain it You don't need a whole cycle to start the atom space change process. All you need is to deliver the energy, and it's the rate of change and the magnitude of the energy that makes the process happen. So once you deliver that, even part of a cycle, you can start that change and you can start to reduce mass or the space refraction that you're looking for. So once you get the antenna up to voltage to where it radiates at a level that you need, the effect on the atoms in the material should happen very quickly with less than one cycle. Okay. Why are we using antennas? Because it's a convenient way of providing the radiation that we need. That's all it is. That's why we have these big antennas going around at the speed of light, because it's providing radiation to atoms that are forming part of the craft. And I just want to point out here that atoms are really small. Avogadro's number gives 3 to the 10 to the 23 atoms for 1 ounce of iron. Stars in the visible universe are 10 to the 22 to the 10 to the 24th. Atoms are really small. So if you take a lot of them and you put them together, you can affect space where they reside in a big way. All right, so one of the things that's key, and this model, for 20 years, I've been trying to find a flaw in this model. And I kept thinking, okay, it's got to be an inertial mass, because if it goes negative, the diametrics would be that Earth would attract negative mass, because if you push on negative mass, it moves towards you according to the accepted Bondi diametrics. Well, we're going to throw all that out the window, because that's not what this model says. If I go back up to this equation and I try, and I solve this equation for Mi, and I say, okay, what's happening to Mi? Well, I can't really come up with absolute numbers on that, because I could if I went back to my spreadsheet and I went through all kinds of calculations and got U's and VPs, but I don't need to do that. And the reason I don't need to do that is because if I solve this guy for Mi, it basically shows that if I can put in integer values of mg, in other words, make mg equal minus 3 mi, 5 mi, 0 mi, equal to mi, I can kind of get a feel for what this equation does. And when I do that, what I find out is, and I'm going to plot mg versus, so what I'm going to do is I'm going to plot 2 over the square root of 3 minus mg, where mg is some integer multiple of mi. So when I do that, I see that the equation comes down very quickly as you get closer to the power density that you need to cause the effect. And then it approaches an asymptote value. I don't know if it's 0, and I don't know if it's a positive number, but I know it's positive. Why? Because there's nothing in this equation that can make it go negative. I'm providing that energy myself, so I know that's positive, and I just keep increasing it. VP is 1 over square root of mu epsilon, and they're just getting bigger, making VP smaller, so they're not going to 0. So there's no way for this equation to go to 0. So if I put mg equals 0 into this equation, I get 2 over the square root of 5 u over VPC. If I put mg equal minus 2 mi, I get, keep in mind that this is a minus sign here, so if you put minus numbers in here, you get positive. So if I put mg equals minus 2i, I get 2 over square root of 21. So that square root of 21's gotten really bigger really fast, which makes this equation get really small really fast, but it's positive small. If I put mg equals mi into this equation, now you get 0 over 0, so it converges, and it converges to unity, which is what you would expect it to do. So this equation just gives you a lot of information about things, about mass. All right, so if you plot this guy and you see that it's going towards some number, you can see it never goes below 0. So what does that mean? That means that when mg goes to 0 and negative, mi always stays positive. Why is that important? Because inertial mass, if it's negative and you push on it, it moves away from you. What does that do? That gives us a way to make propulsion for this antenna. We can use planets, moons, stars, black holes, anything that has a significant gravitational field. We can use it to repel from, create initial motion, reduce mass, create high velocity. All we need. There's no other propulsion in this presentation other than an antenna and a way to power it. And we will see, I'm not saying this explains how UFOs work. What I'm saying is it mimics a lot of their behavior, and you will see that. Okay, now that we know that according to this model, mi never goes negative, what do diametrics look like? Well, get the equations up here. Positive mass attracts positive mass. Negative mass attracts negative mass. Positive mass and negative mass repel each other. That's what this model says. So we're just using the equations as our guide here. We're not injecting any of our own opinions into anything. And I just pointed out here that Bonner, who was one of the negative mass guys, was stating that he was so repelled at the fact that if you pushed on negative mass that moved towards you, that he would prefer that inertial mass always be positive and negative. Well, this model gives him his wish. It's always positive. All right, so what do we get? If I can get this on here. All right, here's what this model gives us. We have a prolate antenna, which is the gray part here, with a tiny little blue insulator. You want this gap to be very small because you want the electric field across it to be highly in integrity, because that's what makes the physics work of the antenna. Now, this is just a sphere that you squashed. And you know, at the first presentation, I talked about drawing a sphere into a cigar or pushing it into a saucer. I gave data on drawing it into a cigar, and it has natural resonances, which I'm guessing is what these craft operate at, because it makes the electronics way more simpler. If you squash it into a field, since you're starting with a sphere, it should exhibit some kind of resonance also. So that's the geometry we're using here. So this is a saucer. We're looking at the edge view of it. And the radiation profile of a saucer, you're going to get more radiation at the center, top, and bottom than you do at the edges. That's just the nature of the radiation pattern of the saucer. It doesn't matter what you make from an antenna like this, it's going to have this radiation pattern because that's the nature of this antenna. So what I'm saying is, you've got an antenna that's radiating energy that is reducing the mass of the antenna. So the first presentation, we talked about the fact that we live in an analog universe, and analog implies curvature, which implies distance. So we're saying that there's a distance beyond the edge of the craft where the mass reduction is still in effect, and that affects the atmosphere around the craft. And so what I believe is that that has something to do with the cold plasma that you see around the craft. I think what it's doing is it's instantly accelerating air molecules and atoms. And the fact that you have negative mass means you're going to get repulsion in the atmosphere itself, which is going to cause turbulence. So it's hard to understand exactly what the dynamics of that plasma is according to what I'm presenting. It could be that it's more to it than that. I'm not sure that Lamore, which is what I presented last time, could explain all of it. I think there's more to it than that. But at any rate, you have the surrounding cold plasma, and you have the larger negative mass plume at the bottom just because of the radiation. This is more rounded, but this is what I've come up with here for what I was able to do. And you can see that the ice cream cone is on the bottom. I'm pointing, okay, here. I'm pointing ice cream cone from Hill's circa 1980 book, which I consider very credible. And he has a chapter in that book where he actually describes, and I quote, ice cream cone shaped cold plasma plumes below hovering craft. This is 50s, 60s, 70s data that he collected when he was working at NASA. It's an interesting story. The story I read was his daughter found the notes after he passed away and published them. But at any rate, I encourage everyone to read his book. So anyway, back to this guy. So we've got the plume here. So we've got negative mass on the bottom, and of course the Earth is repelling that. So we've got vertical lift, is pushing, but the craft is falling up. Well, we don't want to do that. We want to hover. So we got to provide some counter mass to compensate for that. Well, you could say that these guys are really smart that are doing this, and that they're coming up with some kind of phased array, high resolution beam control on their antenna. And I don't know how to do any of that. So my plan B is control the material science of the antenna, the radiator. So you got three parms, sigma, epsilon, and permittivity and permeability mu. Sigma, conductivity, I'm not sure how to control the conductance of a conductor. So we're going to X that guy out. Permittivity, it only has, most things in nature are less than 10, so you've got only one dynamic range to work with. So we're going to X that guy out. Permeability, well, guess what? You can control metal with a magnetic field. And it can go from like unity to maybe 100,000. Pure iron that's annealed almost perfectly can get permeabilities close to 1 million. So you've got plenty of dynamic range to work with. You've got a way to couple in energy into it that affects the permeability so you can control it. So that's what we're going to do here. We're going to have some, and don't probe details here because I really don't know. I'm just presenting concepts. So you have some kind of magnetic field control here that can deliver a field to the different parts of the antenna, reducing the permeability of that part of the antenna. When you're trying to radiate at 1 hertz with something that's maybe 30 feet in length, the antenna is extremely electrically small. And electrically small antennas have incredibly small radiation resistances, way smaller than the ohmic resistance of the metal that is the antenna element. So usually 99.999% of all energy is dissipated as ohmic heat, and hardly anything gets radiated. Well, what we need to do is we need to figure out a way to really increase the radiation resistance so it's higher than the ohmic resistance. And oh, by the way, we'd like to keep the ohmic resistance as low as we can. So what we can do there is with the magnetic field, let's say we have this antenna and we figure out a way to make it radiate. We've got a really fairly high radiation resistance, higher than the ohmic resistance. So we got a pretty good efficiency, and so the craft is operating fine. Now all of a sudden we want to dampen part of it. Well, if we reduce the radiation resistance of an antenna is proportional to the permeability of the environment of the antenna, the element and the environment. So if you reduce the permeability, you'll reduce the radiation resistance, which will reduce the radiation. So you can actually control how much this antenna radiates in regions by controlling the magnetic field of that region. If you look at permeability curves, you can either control off of the linear area before the plateau, or even if you're on the plateau, you can use saturation to control it, even though that's sloppy. But at any rate, now we have a way of actually controlling the radiation of the top half of the antenna, so we can keep that mass positive. So now you have negative mass being repelled by the Earth. You've got a positive mass on top, which is acting as a buoyancy weight. So now you can kind of determine how much vertical lift you want by adjusting these parameters. So now we have something that is controllable in atmosphere and in a gravitational field. Now we want to be able to tilt it. We'll learn why later. So let's see how we would tilt that. Well, okay, I'm looking at the top here of the craft, and this is the magnetic control. So let's say I just take a pie slice out of this guy and make it normal so that it radiates more than the surrounding area of the antenna. Well, okay, this is going to have negative mass now, so it's going, or at least a mass that's different than what the rest of the positive mass around it is. So it's going to be repelled by the Earth, where over on the other side it's going to be attracted by the Earth, or a planet, or a moon, or a star, and you're going to get a rotational force. So by changing how you apply this field to the metal, you can change either the buoyancy of this thing, how much it lifts up. Also, you can change the orientation of the tilt of it. All right, so with that said, I can't be 350 already. I just got started. We're gonna have to zoom through this thing. Okay. No, it's not a prototype. Boomers know what this is. In the 50s and 60s, we all laughed at the Air Force's attempt to make a flying saucer. Well, that's not what this is. I saw a documentary of the pilot who's also the designer, and his story is it was an experiment to verify that stable vertical lift, when tilted, produces a horizontal velocity vector component. And if you look at the old videos from this guy, that's exactly what they were doing. They were tilting it, and you could see it would go horizontal. So what does that mean? Well, if you have a stable vertical lift, you've got negative mass on the bottom of your craft, the planet's pushing it up, it's falling up. You've got positive mass on top, so you're creating a balance there so it stays vertical in a stable position. And then you tilt it. Of course, the resultant here is a little bit more energy, so you're going to have to add a little bit more energy to the vertical to keep it the same height, but you're going to produce a horizontal component, and it's going to go horizontal. Is it 350 already? All right. So with this technique and the vertical lift provided by the negative mass under the craft, we can go up, we can go down, we can go sideways. And if you tilt and you add more vertical lift, you're going to go up at an angle. If you provide less vertical lift, you're going to go down at an angle. So we can go any direction we want with just this. So let's look at what a control curve would look like for a craft like this. Okay, I showed you before the plot of the MI equation. This is the MG equation. But so that I could see how it works side by side, I took the absolute value of when it goes negative, so I flipped it up just so we could see a comparison. And keep in mind, the scale on the left-hand side is a log scale. So you got a big change in this. So the left side of this is low frequency. The right side is higher frequency. But if you remember, power density and frequency were reciprocals of each other. So if you plotted this as power instead of frequency, it would just be the reverse. High power would be on the left, low power would be on the right. When you have low power on the right, you don't have the effect taking place. So the mass is just what you measure, mg. So it's flat here. And if you go way out in frequency or power, if you reduce power to 0, the difference between MI and MG is just really small. I mean, really small. So let's take a look at how this graph would work. Well, if you want to get buoyancy in atmosphere around a planet in the gravitational field, you'd probably make the negative mass a little bit more than the positive mass. It's exaggerated here. This is the left-hand side, the black is the bottom of the craft, the right-hand side, the red is the top of the craft. So now you're adjusting the top and the bottom just so you get a stable height and it stays at that height. Okay, now you set there. Now you want to go fast. Let's say you tilt it, you go sideways now at a small velocity. Now you want to go really fast sideways. Well, you up the power of the antenna, it reduces your mass, and according to conservation of energy, if you reduce your mass, your velocity, kinetic energy equals 1/2 mv squared. So if you reduce mass, velocity's got to increase. Momentum's equal mv squared. If you reduce mass, velocity's got to increase. So by decreasing the mass, you can actually increase your velocity on a log scale. So you can go really fast, really quickly. Now let's say you're in interstellar space and you don't have a gravitational field and you get stuck and you just want to use diametrics. Well, you can make the bottom really big negative mass. You make the top just regular positive mass. So now you have the repulsion of the craft itself on itself. So you get a force and the craft actually accelerates. And of course, you don't need, in that case, you don't need a top and bottom. You could actually flip electronically, you could flip which one was which. So anyway, this is kind of a very crude intro into how one might control a craft like this on a curve. And you could look at a lot of other scenarios on this plot. I encourage you to spend time with it. You can come up with a lot of ideas with it. So what happens to the bottom of the craft while we're increasing power? Well, we start out, it's all positive. We increase a little bit. Okay, we know that the highest radiation is in the middle of the antenna radiator. So that's going to hit 0 mass first. We're still going to have positive around the perimeter. We keep going. We're going to get 0 around the perimeter, negative in the middle. And then we're finally going to get negative on all of it as we get higher and higher power densities. And then if we dampen the center, we can make that positive with the rest negative. Or we can make it all positive if we dampen all of it. And this just shows you how the two carriers would work, the V and the triangle. I'm claiming that the cigars and saucers are radiators, and that the V's and the triangles are being illuminated by the saucers and cigars. So this kind of gives you the pattern of how it would change on the antenna radiator. I'm running out of time here, so I've got to really move on. Okay, this is the concept of a calibrated space refractor. I'm using a superconductor antenna. I'm going to use a kind of a system G here, but instead of using copper and iron filings, I'm moving everything up in conductivity. We're going to use a superconductor ceramic thread and silver. So silver is going to be the surrounding medium replacing the iron powder, and the superconductor threads are going to be the antenna element. And we're hoping to get at least a 3 or 4 magnitude difference in conductivities here, so you don't just short the threads out with the silver. But at any rate, if you could do that kind of thing, you could make the antenna. I have American superconductor antenna wire. I have a 30 meters of it, which is not made anymore. And this is the way it's made. So the idea here is that if you take this superconducting antenna and you radiate into a surrounding shield on the outside, which would be iron atoms, you could make this antenna lose weight. Well, if you used iron as a surrounding shield and you made it 0 mass, you could use our equation from above, which is just a number, to calibrate your scale on this. And if you did it for several elements like nickel and copper, you could get several data points. You could curve fit that. And then all you'd have to do is use one calibration metal to bring that curve and normalize it to that data point. And now you've got a calibrated curve that your instrument can display space refraction for you, so you can experiment with it. I wish I had more time on this, but at any rate, let me get through some of this just so I can make sure I get through it. Why this model like superconducting radiators? This came up last time. This is Maxwell's phase velocity. This has got nothing to do with this model. Put the conductivity of a superconductor into this thing, a ceramic disc, e to the 20th. See what you get for VP. It's amazingly small. So we learned before that we have electrically short antennas. The slower we can make VP, the longer we can make the antenna look electrically. So it becomes a more efficient radiator when we slow down phase velocity. Likewise, radiation resistance is a function of VP, mu and epsilon. So when they get larger with slower VPs, radiation resistance gets larger. And so since we're dividing that with ohmic resistance, the efficiency of the antenna gets larger. We radiate more efficiently when radiation resistance gets larger. So for these reasons, it really makes sense for a 1 Hertz antenna to be superconducting. So large sigma, slow radiator phase velocity, increasing radiation resistance and efficiency. Large sigmas reduce power needed to affect desired MG change. So this is what we're going to do now. This is going to be a prolate cigar. We took a sphere, we're stretching it into a cigar. We know that it has natural resonances, and we know that putting VP in here as sigma is a very large number will make this antenna a more efficient radiator at low frequency. So we're just transformer coupling the energy into the antenna. We're floating the antenna in a coolant, and we have it surrounded by a high permeability metal like iron, nickel alloy. And we're radiating into it, and we're causing the mass reduction to happen in the surrounding shield. So this would be the idea of how a superconductor radiator would work. We learned last time that at the ratio of 7 to 1 over length to width or larger produces natural resonances of L over lambda of 0.5. So that is kind of an intro into why this model likes superconducting antennas. And last but not least, this is an idea that Ron had from the last meeting about Schumann resonance. And so what I did was I just took what was published on the internet and put my own spin on it. So what we have here is we have some op amp that has super high input impedance, like a Linmos or something of that nature. And we're putting 200 gigohms across it just to bias it, so it's just not floating. And we're using a spherical antenna. Spherical antennas are always capacitance, are always capacitive, but they're broadband. So by putting half of it to one side of the op amp, the other half to the other side of the op amp, you get a differential input here, and the rest of it's just normal electronic stuff. You want a way to control your gain and your offset. You want a cable driver. So everything in the dotted line resides at the antenna on batteries. And then on the other side, you'd have a low pass filter. And I'm claiming I'd want a data logger so I could do autocorrelation offline from the data. And you could make it more elaborate. You could make it like set a threshold and make it automatically trigger the logger. But this is what I plan to build here over the next few months and try to see if I can actually measure some of the radiation that I think I'm getting from my antennas. I don't know how much more time I have here, Tim. I'm going to let you lead me here. But I'm going to go back up to this guy. I'm showing this as a dipole, a split dipole. And in that case, the gravitronic tuner would be configured as a inductive gyrator. If you use this as just a current loop and just made it all just a loop, you'd have to configure the gravitronic tuner as a capacitance multiplier. I've tried both of those. They both work really well. And like I said, I can get resonances down to 1/10 of a hertz with values that are usable. But at any rate, so with this model, basically, I really like this. I wish somebody could build this. So basically, you come up with a number based on the iron or the nickel or whatever that you're using here. And with that information, and you know that that's happening at 0 mg, you can actually go in and calculate a number for that particular setting on your instrument. And this would be a very powerful way to measure space refraction in a controlled way that allows people to experiment with it and try to understand more about it. So that's about it, Tim. I don't know that I'm going to have much more here about going through more stuff that's just repetitive. So I'm going to call it quits if that's okay with you.
Absolutely, sir. Absolutely. Okay, well, let me do this then. Steve, oops. Okay, let me stop your screen sharing. And I'm going to put things on gallery view. And everyone, we have a full house here. Everyone, please put your hands together and give Mr. Steve Burns an enormous hand. Steve, thank you. That was incredibly detailed. I mean, super technical. So you lost me like 5 times over, but in a wonderful, good way.
Well,
so thank you,
sorry
sir.
about that. I've talked a lot about this, but I haven't gone through the details, so I did it this time.
Oh yeah, no, I appreciate it. I appreciate it. Well, keep in mind that you are a nuclear engineer and I am most certainly not. So